Good morning, students. This is Arvind, Assistant Professor, Department of DBS Kavali. So, in the previous class, I am discussed for testing of DC machines. So, in that class, I discussed some various tests to be performed on the DC machine. Okay. In those tests, I discussed about two tests. That is a brake test, direct test, direct loading test, and next one is um, and next one is a Simmons test, that is no load test. And now I'm going to discuss two more tests, that is Hopkinson test and a field test. Okay, so coming to that one. So this test is called regenerative or back-to-back test. Okay, this Hopkinson's test is also called regenerative or back-to-back test. So which can be carried out on two identical DC machines. So here I am using two identical DC machines. So actually in the previous two tests I am only take only one machine, but here in this case I am going to take two DC machines. Those two are mechanically coupled to each other and simultaneously tested. Okay, so thus the full load test can be carried out on two identical shunt machines without wasting their outputs. Without wasting their outputs. So one of the machine is made to act as a motor while the other as a generator. Okay, one of the machine is made to act as a motor while the other as a generator. So here the mechanical output obtained from the motor, you know already this one. So motor is a machine, so which is used to converts the electrical energy into mechanical energy. That's why we are getting mechanical output from the motor. So motor drives the generator whose electrical output supplies the greater part of input to the motor. So you know the generator is a machine which converts the mechanical energy into electrical energy. So that electrical energy I am taking output to generate greater part of the input to the motor. Okay, so here the motor input is the electrical energy and generator input is the mechanical energy. So that mechanical energy is given from the is taken from the motor, and the electrical output is given to the motor by using the generator. So here we are using two machines, one act as a generator and one act as a motor. These two machines are mechanically coupled to each other. Okay. Next, the motor is connected to the supply mains. So here the motor is connected to the supply mains only to compensate for losses. Since in absence of losses, only to compensate for losses since in absence of losses. Okay. The motor generator set would have run without any external power supply. So here we are not using any external power supply. So here we are using motor generator set. Okay. So, but due to losses, the generator output is not sufficient to drive the motor. So, but due to losses, the generator output is not sufficient to drive the motor. That's why thus motor takes current from the supply to account for losses. So, due to losses, the generator output is not sufficient to drive the motor. So, to drive the motor, we have to take the current as much as possible. So, that's thus motor takes current from the supply. Why? Because the motor is connected to the supply mains. Okay, the motor takes current from the supply to account for losses. Okay, next. So, this is the diagrammatic representation of Hopkinson test. So here I am taking one motor and one generator. So this motor, so it consists of the armature terminals, that is A1 and A2, and the generator. So these two are the mechanically coupled to each other, generator and motor. So here we are using three ammeters, A1, A2, A3, and we have to calculate the current, that is I1, I2, I3, and I4, like that. So here, if you see this diagram, so here we are using the supply voltage V, and next here I am taking the motor. So this motor consists of armature and field winding. So here the field winding of the motor is connected to the ammeter A2, and it is used to calculate the I4 current, and this field winding of the DC motor is connected to the variable resistor. Okay, and next here I am using the one ammeter. It is directly connected to the supply, so it produces the I1 current, and this I1. And next we have the one switch is there. So across the switch we are connecting the voltmeter. Okay, So here the I1 current and I2 current is entering into the motor, that is I1 plus I2, and next we have the ammeter A3. So this one, so this is used to calculate the current I3. So here the generator also consists of the two windings, armature winding and field winding. So here the field winding is also connected to the variable resistor, that is R2, and this field winding also connected to the ammeter A4. Okay, this is the diagrammatic representation of the Hopkinson test. Okay, next, so the figure shows the connection diagram of the Hopkinson test, that is the previous diagram in the last slide. So here we are using two shunt machines are connected in parallel. So one is motor and one is generator. So the two shunt machines are connected in parallel. So one of the machine is then started as a motor. So I already said this one. So one of the machines is then started as a motor. Here the starter connections are not shown for simplicity. So here in the diagram, there is no connection, starter connections. Okay. So if you have that connections, you will confuse. That's why they are not shown. Okay. So at this condition, the switch S is kept open. So the switch S is kept open. So the other machine which is coupled to first will act as load on first, which is acting as a motor. Because the other machine which is coupled to first will act as load on first, which is acting as a motor. So thus second machine will act as a generator. So I already said these points. Okay, one machine is act as a motor and one machine is act as a generator, and the speed of the motor is adjusted to normal value with the help of the field rheostat. Okay, the speed of the motor is adjusted to normal value with the help of the field rheostat, and the voltmeter reading is observed. Okay, the voltmeter reading is observed while adjusting the field rheostat, and the voltage of generator is adjusted by its field rheostat. The voltage of the generator is adjusted by its field rheostat, so that voltmeter reading is 0. Okay, so this will indicate that the generator voltage is having same magnitude and polarity of the other supply voltage. That's why we are getting the 0 readings on the voltmeter for the generator, not for motor. And next, this will prevent heavy circulating current flowing in the local loop of armatures on closing the switch. Okay, this will prevent heavy circulating current flowing in the local loop of armatures on closing the switch. And next, now the switch S is closed. After that, we have to close the switch. So the two machines can be put into any load by adjusting their field rheostats. So actually we are having two field rheostats, one is for the motor and one is for the generator in the diagram. So by using the two machines can be put into any load. So here we are applying any load to those two machines by adjusting their field rheostats. By using those field rheostats, we are applying the load. And the generator current I2 can be adjusted to any value by increasing the excitation of generator. Okay, the generator current I2 can be adjusted to any value by increasing the excitation of generator or by reducing the excitation of motor. So increasing the excitation of generator or by reducing the excitation of motor, we have to adjust the current generator current value I2. And next, the various readings shown by different ammeters are noted for further calculations. So in that case, we are using 4 ammeters. So the various readings shown by different ammeters are noted for further calculations. And the input to the motor is nothing but the output of the generator. So you already know this point. The input to the motor is the mechanical, so the input to the motor is the electrical energy, and the output of the generator is also the output of the generator is also the electrical energy, and small power is taken from the supply. Okay, and small power is taken from the supply. Here the mechanical output given by motor after supplying losses will in turn drive the generator. Okay, the mechanical output given by motor after supplying losses will in turn drive the generator. Okay, next. So coming to the calculation of efficiency by Hopkinson's test. So previously up to now we discussed about the working of the motor generator set for the Hopkinson test, and now coming to the calculation part. So to calculate the efficiency for the test, we have to take the values. parameters like voltage, that is V, there is a supply voltage, and I1 is current taken from the supply, and I2 is the current supplied by generator, and I3 is exciting current of generator, and I4 is exciting current of motor, and Ra is resistance of armature of each machine, and eta is the efficiency of both generator and motor. Okay, these are the parameters we are going to use to calculate the efficiency of the Hopkinson test. So here the input to the motor. So input to the motor is the electrical energy. So here that is V into I1 plus I2. Okay, V into I1 plus I2. So here I1 plus I2 is the supply current I1, and I2 is the generator supply current. Okay, so input to the motor, that is V into I1 plus I2. If you see the diagram, you will understand this on V into I1 plus I2, and output of motor, that is the mechanical power. So here I am taking the output power, that is efficiency into input, so that is equal to eta into V into I1 plus I2, that is the output of motor. And next, the output of motor will be given as input to the generator. So you already know this point. So the output of motor will be given as input to the generator. So that is input to generator is equal to N into V into I1 plus I2. N into V into I1 plus I2, that is the input to the generator. And coming to the output of generator, that is N into input, that is equal to N into, you already know the input to the generator, that is N into V into I1 plus I2. So from this one I am writing N square into V into I1 plus I2. Treat this one as first equation, and the output of generator can also be given as output of generator is equal to V into I2. Output of generator is V into I2, and input to the generator is N into V into I1 plus I2. Okay, by using these two equations, we have to calculate the eta value, that is eta square into V into I1 plus I2, that is equal to V into I2. And from this one I am writing eta square is equal to I2 by I1 plus I2, and next eta is equal to root of I2 by I1 plus I2. Okay, next, but the assumption of equal efficiencies of two machines is true in case of only large output machines, where difference in armature currents of two machines is not large. Okay, is not large. Next, also the difference in excitation current required to circulate full load current in the armature will not affect iron losses. Okay, also difference in excitation current required to circulate full load current in the armature will not affect the iron losses. But in case of small machines, the difference between armature and field current is large. Okay, so efficiencies cannot be assumed to be same. So here the stray losses are assumed to be equal, whereas armature and field copper losses are separately determined for estimating the efficiencies separately. And coming to armature copper loss in the generator, that is a combination of I2 and I3 currents, that is I2 plus I3 whole square into Ra. You know the armature copper loss formula, that is Ia square Ra. So here the current is I2 plus I3 whole square into Ra, and armature copper loss in motor, so that is the combination of I1 plus I2 and difference of I4, that is I1 plus I2 minus I4 whole square. This is for the armature copper loss in the motor. And next, copper loss in field winding of generator, that is V into I3, that is the field winding copper loss, and copper loss in field winding of motor, that is V into I4. But total losses in generator and motor are equal to the power supplied by the mains. Okay, so power drawn from the supply, that is equal to V into I2. So the stray losses of both machines can be calculated as total stray loss for both the machines is equal to V into I2, that is the power drawn from the supply, that is V into I2 minus I2 plus I3 whole square into Ra, that is the armature copper loss in generator, plus armature copper loss in the motor, that is I1 plus I2 minus I4 whole square into Ra. And coming to the copper loss in the field winding of generator, that is V into I3 plus copper loss in the field winding of motor, that is V into I4, that is equal to WS, that is the total stray loss for both the machines. Here it consists of generator and motor. Okay. Next, assuming that stray losses are equally divided between the two machines. So previously we calculated the total stray losses for both the machines, but here assuming that the stray losses are equally divided between the two machines. So stray loss for each machine is Ws by 2. Okay, next the machine which is acting as a motor, in that one the total losses is equal to I1 plus I2 minus I4 whole square into Ra plus V into I4 plus Ws by 2. Here the input to the motor is equal to V into I1 plus I2, and efficiency of motor, that is equal to eta m is equal to output by input, that is equal to, we know the formula to calculate the output power, that is the input minus total losses by input. Okay, this is the efficiency of motor. And next coming to the E time, that is equal to, so the formula is output key is input minus losses. That is here the input power is V into I1 plus I2 minus of I1 plus I2 minus I4 whole square into Ra plus V into I4 plus Ws by 2. That is input power minus total losses by output power, that is input power is, that is V into I1 plus I2. So output power by input power. So here the output power is equal to input power minus total losses, and by input power, that is V into I1 plus I2. And next the machine which is acting as a generator, total losses is equal to I2 plus I3 whole square into Ra plus V into I3 plus Ws by 2. So output of generator is equal to V into I2. Efficiency of generator is eta G is equal to output by input, that is equal to output by, here to calculate the input, we have the formula output power plus total losses. So from this one I am writing eta G is equal to output power is V into I2 by output power is V into I2 plus total losses is I2 plus I3 whole square into Ra plus V into I3 plus Ws by 2. And next, advantages of Hopkinson test. So here this test requires very small power compared to the full load power of the motor generator coupled system. Here the temperature rise and commutation can be observed and maintained in the limit, because this test is done under full load conditions, and change in iron loss due to flux distortion can be taken into account due to the advantage of this its full load condition, and efficiency at different loads can be determined by using this Hopkinson test. And coming to the disadvantages of Hopkinson test, first one is it is difficult to find two identical machines needed for Hopkinson test. Okay, and next both machines cannot be loaded equally at all times, and it is not possible to get separate iron losses for the two machines through they are different because of their excitations, and it is difficult to operate the machines at rated speed because field currents vary widely. And coming to the next one, that is field test. So this is one of the methods of testing the DC series motors. So this is applicable to the series motors. And unlike shunt motors, the series motor cannot be tested by the methods which are available for shunt motors, as it is impossible to run the motor no load. So if you want to run the DC series motor, you have to apply the load. Okay, so it may run at dangerously high speed or no load. That's why we have to connect the load. Okay, in case of small series motors, brake test may be employed. Okay, the series motors are usually tested in pairs. Okay, so the field test is applied to two similar series motors. So here we are using two similar series motors which are coupled mechanically. The connection diagram for the test is shown in the figure. So here I am using the generator and motor set. Okay, two similar series motors or two similar generators also we are using. So this is the connection diagram for this test. So here I am taking the supply voltage from the DC supply V, and next we are using one motor. So it consists of armature and field winding. So here the armature winding consists of one voltmeter, and the motor series field consists of an ammeter to calculate the series field current, and it consists of generator series field to the armature terminals of the motor. And next we are using the generator, and these two machines are mechanically coupled to each other. And next we are using the generator, so it also consists of two windings. One is field winding. This field winding, generator's field winding, is connected to the motor armature terminals, and next the voltmeter is connected to the variable resistor R. So by varying the variable resistor, we have to note down the voltage readings and ammeter readings. Okay, so the armature winding of the DC generator is connected to the ammeter, Okay, this is the connection diagram for the field test. And as shown in the figure, one machine is made to run as a motor while the other as a generator, which is separately excited. And the fields of two machines are connected in series. So if you observe the diagram, the field windings of the two machines are connected in series so that both the machines are equally excited. And in the previous Hopkinson test, the two machines are not equally excited. Okay, so this will make iron losses same for the two machines. But in the Hopkinson test, there is the difference in the iron losses because of difference in the excitation. But here the excitation is same for the both the machines. So this will make iron losses same for the two machines. So the two machines are running at the same speed. Okay, the generator output is given to the variable resistor R. So the generator output, that is the mechanical power, is given, electrical power is given to the variable resistance R, and the variable resistance R is changed until the current taken by motor reaches its full load value. Okay, and next, so that will be indicated by ammeter A1, and the other readings of the different meters are then recorded. So here, let to calculate the efficiency of this field test, we have to take the parameters, that is V is equal to supply voltage, and I1 is current taken by the motor, and I2 is the load current, and V2 is the terminal voltage of generator, and Ra and Rc is the armature and series field resistance of each machine for motor and generator. And next, power taken from the supply, that is V into I1, you know this one, and output obtained from the generator, that is the electrical power, that is V2 into I2, and total losses in both the machines, that is Wt is equal to V into I1 minus V2 into I2, that is the power taken from the supply minus output obtained from the generator. And coming to the armature copper and field losses, Wcu is equal to Ra plus 2 Rsc into I1 square plus I2 square Ra. And next, total stray losses, that is equal to Wt minus Wc, because here I am taking Ra plus 2 Rsc means, so these two are in the series connection. That's why I am taking Ra plus 2 Rsc into I1 square plus I2 square Ra. So total stray losses is equal to total losses minus copper losses, that is both armature copper loss and field losses. And stray losses for per machine is Ws is equal to W2, that is the total losses on both the machines minus armature copper and field losses by 2. Since the two machines are equally excited and are running at same speed, that stray losses are equally divided. That's why I am taking Ws by 2. And for the motor, input to the motor is V1 into I1, and total losses is equal to armature copper loss plus field copper loss plus stray losses. So here we are having I1 square into Ra plus Rsc plus Ws. This is the armature copper loss and field copper loss plus stray losses. So here the combination of armature copper loss and field copper loss is I1 square into Ra plus Rsc plus stray losses is the Ws. Output of motor, that is input power minus total losses. So here the input to the motor is V1 I1 minus total losses is I1 square into Ra plus Rsc plus Ws. And efficiency of the motor from the above these things, eta m is equal to output power by input power. So here the output power is V1 I1 minus of I1 square into Ra plus Rsc plus Ws divided by input power is the V1 I1. So this is the efficiency of the motor. And coming to the generator, so efficiency of generator is of little importance because it is running under conditions of separate excitation. So still it can be found as follows, that is output of generator is V2 into I2. So it is connected across the load generator. Okay. So that is the output of generator is V2 into I2, and field copper loss is I1 square into Rsc, and armature copper loss is I2 square into Ra, and total losses is armature copper loss, field copper loss plus stray losses. So from this one I am writing I2 square into Ra plus I1 square into Rsc plus Ws. So here I2 square Ra is armature copper loss, and I1 square Rsc is the field copper loss plus stray losses. And next, input to the generator, you know the formula, that is output power plus total losses. So here the output of the generator is V2 into I2 plus total losses is I2 square Ra plus I1 square Rsc plus Ws. And coming to the efficiency of generator, eta G is equal to output power by input power, that is eta G is equal to, here the output power is V2 into I2 by input power is output power plus total losses. So here the output power is V2 into I2 plus total loss is I2 square RA plus I1 square RSC plus W suffix S. This is the efficiency of the generator, and the most important point to be noted is that this is not regenerative method, though the two machines are mechanically coupled, because the generator output is not fed back to the motor as in case of Hopkinson test, but it is wasted in load resistance. This is the only important point to be noted in this field test. Okay, thank you. So in the next class, I'm going to discuss another method is there. Up to now, we discussed 4 tests. One is brake test, and another one is Swimmer's test. And after that, we discussed Hopkinson test and field test. And one more method is also there. That is a retardation test. I will discuss this one, that test in the next class. Okay, thank you.